let me delve right in. I'm just going to move some furniture here. So I will be talking today about all kinds of different heat mitigation strategies we can use here in the valley to cool the environment for people who live here, anywhere from turf, because there was a special request to talk about artificial turf. I'll show you some measurements that my colleague Jennifer Vanos and I took in various places, and then I'm going to transition to trees and other types of heat mitigation efforts. And I will present two tools that we're using for this type of research. One is MaRTy. MaRTy is currently not here. MaRTy is hibernating because his temperature probe is broken. But ANDI is here, not in this room, but ANDI is upstairs. And as Anne mentioned, we'll have Dr. Ankit Joshi join in about half an hour. We have the principal investigator of the ANDI project, Konrad Rikaszewski, right here. He can answer questions at the end as well. So we'll take a tour of ANDI after this presentation for all of you who are in this room or are interested in ANDI. Of course, this is not working. Let me see if I can change the focus real quick. Yeah, no, it's working. Okay, so I'm an associate professor with the School of Arts, Media, Engineering, and I direct the SHADE lab here at ASU. SHADE has a double meaning. Of course, it means shade, but it also stands for sensible heatscapes and digital environments, because I have a joint appointment with computer science. And in my lab, we look at heat from three different aspects. We look at heat, how you can sense it using instrumentation. I'm not sure if this pointer is working well. It's okay-ish. So we use instruments to measure heat, such as MaRTy and ANDI. We also look at how people experience heat as they're pedestrians or unsheltered populations outdoors. And then for all the cases where we cannot use instruments or humans, we use computers to essentially model the heat and look at different scenarios, what we can do to mitigate heat, and so on. I don't have to tell you that it's very hot here. This is a summary of our summer of 2023. Hopefully this summer is not going to be as brutal. We don't know yet. We broke the record for the most 110-degree days last year, 55 days. Actually, 31 of those were at a stretch. It was the complete month of July. We also broke the record of the average daily temperature in July. We broke the record again in August. And also very significantly here for this era, we broke the record for the warmest summer low, which was 97 degrees 2 nights in a row. So that means the temperatures did not cool down below 97 degrees Fahrenheit 2 days in a row. And we're actually just waiting for this moment or for this year when temperatures do not drop below 100 degrees. Luckily, we're not there yet. Sometimes, oh, did you change the focus? Okay, well, so the good thing is if it's hot, you can bake a lot of things in your car. So you can, people have tried to bake pizza. This is me baking cookies in the car. Do not recommend, because your car smells like cookies for 2 months, and the first week is really amazing, and then you get really, really annoyed by the smell. So don't try this at home. This is a person in Austin, Texas, baking a bread in her mailbox, but you can envision that these types of temperatures are really not safe for people outdoors. And that's what happens when it's hot. This is a statistic for the Maricopa County heat-related deaths over the past 12 years. This red bar I added, I think there's an updated figure out there already. So we have 645 confirmed deaths in this area for 2023. And we're expecting 2024 to be in the same range. So now what can we do to mitigate this heat outdoors and make it safer for people? So I will, first of all, this is an overview of the presentation. I will talk about different types of temperature, because when we say it's hot, we can mean different things when we talk about temperature. I will show you some pictures of MaRTy, introduce what MaRTy does, and then because there was a specific request to look at artificial turf, I will show you some measurements of MaRTy and other instruments of this turf, asking the question, is turf actually green infrastructure? It looks green, but we'll see. Then I will delve into shade. Some of you have seen some of those results already. It was MaRTy investigating different types of shade here in this area. I will touch on some cool pavement measurements. And then I'll show you some pictures of ANDI. And then if you would like to go on an ANDI tour, we just have Dr. Ankit Joshi join in the back. He is going to provide you with an ANDI tour right after this presentation and after the Q&A. So when we talk about temperature and we say it's hot, we can mean different things. Usually, when the average person talks about temperature, they mean air temperature, and that's the actual temperature of the air that's surrounding us. That's the temperature we see on our phone app when we look at the weather forecast. That's the temperature the news reports to us, but it's not really the most important temperature when it comes to a person's experience of heat. The other type of temperature is surface temperature, and you may have seen some high-resolution temperature maps for either Phoenix or other parts of the world. So those maps are usually derived from satellite imagery. So there's a satellite, essentially a humongous thermal camera that looks down onto the Earth, and it measures the temperature of the surfaces. Sometimes it's also called skin temperature. So that's the temperature. Well, if there was a satellite here, the temperature of the table to the touch would be the temperature of the asphalt parking lot to the touch. But again, this may not be the best metric if you're thinking about people, because we are standing under a tree, not on top of a tree, and we don't really experience the asphalt temperature. Well, we have the heat radiated at us, but we're not laying flat on the asphalt. So surface temperature is really not the best temperature when it comes to heat representation. So now we have a third temperature, and that temperature concept is fairly new. Some of you in this room are familiar with this already. It's called the mean radiant or radiant temperature. And that's the heat load that the body experiences from all directions, top, down, left, right, front, back, when we're outdoors or even indoors. And there's a schematic right here. So this little guy is running over some I don't think this is turf, I think this is real grass, and you can see all the different heat sources and heat sinks that this person is exposed to. So this mean radiant temperature is trying to capture all these radiative influences. So now envision you are outside. It's a day cooler than today. It's only 105 in this example. Today it's going to be 111. And imagine you're standing on this parking lot. This is the former Mirabella parking lot. Now there's Mirabella over there. And then on the other side, maybe you're standing on this grassy surface that's under this big tree. This is somewhere on ASU's campus. So if you're standing on this parking lot right there, like MaRTy, you might feel it's 125, but if you're standing in the shade under this tree, you might feel like it's only 98. The air temperature hardly changes between these two locations. It might be 2-3 degrees different, but the experience temperature you feel is way different. And this is what MaRTy can measure. So this is the MaRTy card. MaRTy stands for MRT, which means mean radiant temperature, and that's what MaRTy measures. MaRTy has these net radiometers. These are radiation sensors that face in 6 directions, and they capture the shortwave radiation and the longwave radiation. In terms of the shortwave radiation, you can envision this as the visible sunlight and the UV radiation that hits your body from all directions. And then the longwave radiation would be the heat that comes off of hot surfaces. So when you're standing on this hot asphalt parking lot in the summer, and you can feel this heat radiating at you, that's the longwave radiation. So MaRTy can measure this. MaRTy is a regular garden card with these weather instruments. MaRTy has a X or Twitter account. If you would like to follow MaRTy on X, you can do that. And MaRTy has been helping us a lot over the past, I would say, 8 years or so, since he was born in 2016. Yeah, so that's 8 years, to investigate different heat mitigation strategies here in the Phoenix area. So now when I talk about heat mitigation strategies, there are broadly 3 things we can do to cool our outdoor environment. The first strategy would be we can plant trees, we can put more grass, we can broadly use urban greening to make things cooler, because vegetation breathes and sweats and evapotranspirates like we do, kind of. So if we introduce more green spaces, we cool the environment, but on the flip side, we also require more water to sustain these landscapes. The second strategy is we can change urban materials. So we can change the reflectivity of the surface or the color of the surface to make it more reflective, to reflect some of the energy that the sun if the sun hits the surface, so that some of that energy is actually reflected back into the atmosphere and not stored in that surface, so that potentially cools that surface. Again, this is the surface temperature, not the air temperature. And then lastly, we can change the urban form. We can design buildings that are taller, create more shade. We can change the arrangement of the buildings. There's some research in Singapore where they actually, when they built the marina, they arranged the buildings so that they would channel the wind from the ocean into the city. So we can use the arrangement and types of buildings to influence our heat profile. So now let's delve into urban greening. And this was a question I think that came up in this working group. Is turf actually green infrastructure? So here's a schematic that my colleague, Dr. Vanos, developed for one of the outreach activities. And it shows you essentially how grass reacts in the heat and how artificial turf reacts in the heat. These numbers are just rough estimates. They're not true numbers. They're just to show the concept. But what happens is if the sun hits your real grass, the real grass heats up. Some of the sun's energy is reflected. Grass has an albedo of about 20–25% or so. So some of that energy is reflected back by the grass. Some of that energy is stored in the soil, but our grass here is usually irrigated. So that means there's water content in the grass. The water actually is cool when you apply it to the grass. So the soil is relatively cool. Then this grass evapotranspirates. So some of that energy is actually used to evaporate water. And then whatever is left and whatever is stored in the soil gets released from that grass. So in this example, this says 25 heat units, whatever these heat units may be. So now here's your artificial turf. Same thing, same amount of energy hits the turf. So now the turf has a slightly different albedo, but same as the grass, some of that energy gets reflected back into the atmosphere. But most of that energy actually gets stored in the surface under the grass. This heats up, the grass itself heats up, and then most of that heat is actually then released as long wave radiation back up. And I can show you some pictures. So here are some rough numbers of measurements. If this is the surface temperature of your artificial turf, this can reach up to 160 to 180 degrees Fahrenheit, whereas your real grass is only 98 to 100, and this was at a roughly 105 degree day. So here are some visuals, again, from my colleague, Dr. Vanos. This is a synthetic turf football field. This is a picture that was taken with a FLIR thermal camera, and you can see the temperature readings up here for the artificial turf are 164 degrees Fahrenheit. And in this picture here, the artificial turf is about 153 degrees Fahrenheit. You can see this is not really a safe surface to play football on if you're a football player. So my colleague and some of her students also did a study on some of these football fields where they had installed this artificial turf. They put up a weather station. Here are the measurements. You don't necessarily have to look at these bars. They show you the various fluxes that come off of that surface, but I would like to direct your attention to these red dots right here. The red dots designate the surface temperature of the artificial turf, which is the temperature to the touch. And you can see the artificial turf is at around 140 degrees Fahrenheit. And then you have your blacktop, which is an asphalt surface, which actually has a temperature, a surface temperature that stays below the artificial turf. So artificial turf can get hotter than asphalt in the summer. I think this was in Texas. This was another experiment at ASU. This was on the design school's roof. My colleague, Paul Coseo, and again, Dr. Vanos and myself, we had a small seed grant looking at different types of artificial turf in these small plots. And what we found was actually that the regular artificial turf was not hotter or cooler than what was called a product that was called cool turf. They were all equally hot in this experiment. And here are the raw data. Again, this is a very busy slide, but what I would like to point out is the yellow and the orange lines here. Those are the surface temperatures of the regular synthetic turf and the cool turf. So you see they track each other fairly well. So there's no benefit in choosing different types of cool turf over other types of cool turf. So this was probably 5 years ago, so there may have been some recent developments, but at least at that point, there was no benefit one type of turf over the other. And then lastly, we had MaRTy out in the Mill Avenue district. This is the Pedal House Brewery. They had an artificial turf patch in front of the brewery. We took MaRTy out to this Mill Avenue district to measure different surfaces. We measured the air temperature, surface temperature, and mean radiant temperature over all these surfaces. We looked at brick, asphalt, and artificial turf. And it was a day that was as hot as it's going to be tomorrow, 114 degrees Fahrenheit. It was fairly hot back in 2017. And then here are the numbers. This is the time of day. Each row is a different time of day. The surface type is, no, each column, sorry. And then each surface type is listed here. And then if you look at the air temperature values, you could see that these triplets here belong together. Each transect was a triplet. So they're very similar. So that means that the air temperature over these surfaces within 1 hour did not vary a lot. But what varied was the mean radiant temperature over these surfaces and also the surface temperature of these surfaces. And if you look at these numbers here, again, you find the same pattern as my colleague Dr. Vanas found, that the artificial turf gets hotter than the asphalt surface during the day. So you see there's a common pattern. This was in Arizona. The other measurements were in Texas. So artificial turf gets really, really hot. There are other drawbacks, and I'm not a chemist. So I cannot really speak to the chemical impacts of this turf. But broadly speaking, the turf does not sweat or transpire like your true grass would be. There are some flooding concerns as well. It's difficult to combine the artificial turf with other natural plants, such as trees. It's not really a true habitat for animals because it's plastic. It's too hot to walk or play on, and you saw that from the numbers I just presented to you. It's really not safe for anybody to touch the surface with their feet or their paws during midday. You will have to clean it with water, and also if it gets too hot, you actually have to cool it down with water. I think there's a park in Scottsdale, Cavalier Park, where they used artificial turf and then they had to water the turf to cool it down, which means, well, you might as well just put grass. And yeah, so there's lots of maintenance. You have to clean it. It looks really dirty when there's some leaves on the grass, or turf, I should say. And it's a harder surface, so it's not as soft and bouncy as grass. And I'm happy to take some questions about all of these things, but I can mostly speak to the heat portion of the turf. But as a heat researcher, I would not recommend to place turf anywhere where you socialize, play, or use these surfaces in any way. Okay, so that brings us to what's a better solution, right? So turf does not seem to be the best solution to cool people down. It might look green, but it is not really green infrastructure. So one of the best solutions here in the valley, because it's a very dry and very hot heat, it's not very humid, the best solution is shade. This was from a recent piece my colleague Kelly Turner from UCLA led, and you see there's a pattern. My colleague Dr. Manas is on this paper as well. So here is a schematic of 2 people at a bus stop. One person is standing in the sun looking at their phone. The other person is standing under the bus shelter. So now what happens is that there's the same amount of heat coming down onto these 2 people. So you see the long wave radiation and the short wave radiation. In the case of this person with the phone, this person gets directly hit by the direct sunlight and all the radiation that comes from above. Also, because this surface here is sun exposed, the surface heats up and radiates or re-emits the heat towards the body. That was the case that I explained when you're standing on this hot asphalt parking lot and you can feel the heat creeping at you. Also, some of that radiation that comes from the sun, because it's a lighter surface, it's a concrete surface, might get reflected also towards the person's body. So this person gets this radiation really from all directions. This other person here under the bus shelter, much smarter, the bus shelter gets hit by the sun, heats up, and then re-emits some of that heat towards the person. But the portion that's being re-emitted from this hot roof is much smaller than the heat that this person with the phone receives from the sun. Also, the surface under the shelter does not heat up as much because it's shaded. So there's much less heat that's radiated back at this person's body. So you can see shade is really, seems to be a really great option to keep people cool. So now we could just plant more trees, right? Simple as that. Cities in Tempe, Phoenix have tree and urban forestry plans that aspire 25% tree canopy cover, but it's just the toughest thing to plant trees in this environment. Trees don't really like being on a parking lot. There's just not a lot of space to plant trees. There are power lines above ground, underground, sewer lines, internet cables. So it's just difficult to plant trees. So now the question arose, can we provide shade by other means in places where it's just difficult to plant or to maintain those trees? And so this is how this 50 grades of shade study came to be. We took MaRTy out here in the valley, in Phoenix and Tempe, to different locations that were shaded in one form or another. So we categorized the type of shade into natural shade. That would be your trees, palm trees, which are, it's debatable if those count as trees, ficus trees, palo verdes, different desert adapted trees. Shade from urban form, this would be anything that is connected to a building, could be an awning, overhang, maybe a shaded walkway, building canyons when you have buildings that are very close to each other and the street is quite narrow. And then the last category was lightweight or engineered shade. So that would be shade from pergolas, from umbrellas, PV structures, anything that's not really related to a building. And then in reference to that, we took MaRTy to some sun-exposed locations to essentially say, what's the benefit of using all these different shade types over being sun-exposed and not shaded at all? And here are the findings. This is organized by time of day. So we looked at the overall daytime. We looked at 12:30 around noon, which is when the sun is highest up in the sky. And supposedly the amount of shade is the smallest because there's, you know, the sun is really right on top of your head. We looked at 3:30 in the afternoon. That's close to the hottest time of day in terms of the air temperature. And then we looked at 8:30 at night, which is just after sunset. These bars here, different colors denote different types of shade. The blue bar is your lightweight or engineered shade, the umbrellas, the shade sails, the PV structures. The green shade is the trees, and then the gray shade here is shade from urban form, which would be buildings, awnings, overhangs, and so on. So now the longer the bar, the bigger the benefit. This is showing you the reduction in the heat load on the human body, or the reduction in the mean radiant temperature. So if you are standing in building shade at the hottest time of day, 3 o'clock in the afternoon, you get the most benefit. You get almost up to 30 degrees, and this is Celsius, so this would be almost 50 degrees Fahrenheit cooling or less heat exposure because of the shade. If you look at all the bars overall, it seems that all shade is great. So you can't go wrong with shade, no matter what shade you use. Doesn't have to be a tree. But surprisingly, shade from urban form and from built structures was actually performing very well. So mind you, this is daytime. Once we get to nighttime, we will have heat retention, right? These surfaces are really heat sponges, especially those buildings. And they will store the heat and then release the heat at night. So the area will be hotter at night in terms of air temperature if you use buildings as shade. But during the day, for pedestrians, it's great. At night, you can see the bars go in the opposite direction. That means that we will have a slight heat retention here. Because what happens is if you shade an area, and the sun sets at night, once the heat wants to release and go back into the atmosphere, the shade blocks this heat release. So it's slightly warmer under these shade types at night. And that's the same if it's a tree or a building or anything, because the heat cannot really escape freely because it's obstructed. So there will be a slight heat retention here. So overall, all shade is great. Shade from urban form works really well. So in areas where you can't plant trees or have other restrictions, you can revert to engineered shade, artificial shade. There was a difference in the type of trees in terms of the shade performance. If you have trees with a very small leaf area density, or trees that are a little bit more sparse in terms of the canopy, obviously they did not perform as well as a ficus tree, but then the ficus tree will require more water. So we're back to the trade-off that I mentioned earlier. So now MaRTy can't go anywhere, right? Because it will take a lot of time and a lot of students, a lot of people time to pull him to all the different locations we're interested in. And so now the question is, can we use computer models to replicate what MaRTy measured? And the answer is yes, we can. So in the past, we've used a model called Solveig. It was developed in Sweden. And it requires a point cloud as input data. Point clouds can be obtained through LiDAR, for example, and there are some data sets for Phoenix and essentially for the whole US that provide point cloud data. And then you build raster layers that denote the building and the tree layer. And then you can run the model as low as a 1 meter resolution to do shadow casting and to calculate the mean radiant temperature at every pixel in your domain. And here is a picture of a recent simulation for the city of Phoenix. This is a 1 meter resolution map that shows you the shade distribution of Phoenix. This data set is available through the CapLTR website, and we're currently working on updating this data set. So if you're interested in shade data, talk to me after the presentation. So before I dive into ANDI, because we don't have a lot of time left, let me also look at another heat mitigation strategy that we looked at with MaRTy, which is cool pavement. The city of Phoenix started this program, I think, back in 2019, 2020, after Los Angeles had successfully implemented cool pavement in some of their neighborhoods. And the way this works is it's a slurry that's applied on top of the asphalt road. It binds to the road, and it has a lighter, essentially a lighter color, not to the naked eye, but in terms of the wavelengths or bands that are reflected back. So it looks like concrete in terms of the color. So this is actually a picture that's a little bit exaggerated. That was right after they applied this cool pavement on the road. If you go back now, it really looks like a concrete surface. But this slurry on top of that asphalt will make the road more reflective. It has a higher albedo compared to regular asphalt. And the idea is that less of that energy from the sun that hits the asphalt road will actually be stored in that road, but more is going to be reflected back into the atmosphere. So that lowers the surface temperature of the road. And then hopefully the idea was that it would also reduce the air temperature over that road. So here are some pictures of Los Angeles. And after Los Angeles had implemented this, the city of Phoenix said, let's do this. They started this in 2020, and we did 2 phases of testing of the cool pavement using MaRTy. We also used this thermal bike that had air temperature sensors attached at 4 different heights to see what's the impact of the cool pavement on the air temperature above the pavement. So now what we found, and these are the findings from LA, but also from Phoenix, the findings are very similar. In terms of the surface temperature, the cool pavement drastically reduced the surface temperature. So that means it's doing its job. It's reflecting more of the energy back into the atmosphere. It's not heating up that much. We found a benefit of 12 to 10, between 10 to 12 degrees Fahrenheit during midday, and then 9 to 16, there was a lot of variation in the afternoon. So it means, great, the surface temperatures of the pavement are cooler. It was fairly similar to surface temperatures of the concrete sidewalk. In terms of the impact on air temperature, unfortunately, we did not see a big impact. we saw about 0.13 or so degrees Fahrenheit reduction in the air temperature over the pavement. And the reason for that is that there's just a lot of air mass over that pavement. There's a lot of things going on. Some people have grass in their front yard. Some people have gravel in their front yard. So it's really tough in the real world and non-ideal conditions to tease out what's the impact of the pavement on the air temperature and then what's the impact of everything else that happens in the surrounding on air temperature. If you were to apply this cool pavement to a much larger surface, such as, let's say, the parking lot at the State Farm Stadium, you would probably see a bigger effect on air temperature. So in this neighborhood, the effect was fairly small. And then lastly, what we found that the mean radiant temperature, which is the heat load on the human body, is slightly increased. It was increased up to almost 5 degrees Fahrenheit because of this added reflection that, as it goes back into the atmosphere, hits your body as you're walking over this pavement. We could not find a significant increase in the UV radiation, so that's a good thing. So if you walk over the cool pavement, you're not going to get sunburn more easily because the UV radiation was pretty much the same as over regular asphalt. So now in conclusion, we are currently trying to work with the city to come up with recommendations on where to put the pavement. Definitely, it should not go in places where you have kids play on a playground or where people use these surfaces to exercise or socialize. It's not much different from concrete, but the real strategy to help to keep people cool would be to provide shade and not to change the color of the surface. Also, if you have locations that are already shaded, the cool pavement cannot do its job because there's not a lot of energy hitting the pavement in the first place. So then the reflected energy would not be that much either. So the pavement must be sun exposed to function properly. So if you think about high-rise downtown areas in Phoenix, for example, or Manhattan, New York, would not be the place to put this pavement because it couldn't do its job. So now I talked a lot about the heat load on the human body and how we can change the built environment using engineered and natural surfaces to try to cool things down. But then the question is, what impact does that have on our body, right? I mean, we can say, okay, so the heat load in this location is less. Does that mean if I'm standing at that location, I'm sweating less? Does that mean my core temperature is going down? We don't know, right? And as much as I would like to all recruit you to participate in a study and put you into the heat for 10 hours and see what happens to your body, that probably would not be the safest thing to do. So now we have ANDI. This is our team, as I mentioned. Konrad is the lead of the team. He was the guy who had the idea, we need an ANDI. And this is Jennifer Van Oss, myself, and then ANDI in the back. You'll meet him in person in just a little bit. So ANDI now can tell us what happens to the human body when the human body is exposed to all these situations that I mentioned above. This is ANDI at the open door day when he's dressed up nicely in his Calvin Klein pants. He looks like this. This is actually an older version of ANDI. You see the cables are coming out of his head. So the new version of ANDI that you will see upstairs has the cables coming out of his butt. This is how ANDI looks like inside. So ANDI does not have real organs, but ANDI has pipes and cables inside. And this is a picture of ANDI sweating. ANDI has a lot of sweat glands distributed across his body, 35 different zones that can be controlled individually. And so, yeah, we will put ANDI out in these hot situations and see what happens to his body. So wrapping up before we actually can meet ANDI, just to wrap up this presentation, urban infrastructure can go two ways. We can use it to cool the environment, or we can use it to heat the environment, depending on how we arrange the buildings, what type of vegetation or greenery we use. Air temperature, that's the problem, is not really the best metric when we talk about people's exposure. Mean radiant temperature would be better in places like Phoenix, but it's difficult to measure. You would need a MaRTy or some other device. There's always trade-offs. That's also an important takeaway. Trade-offs between heat during the day versus heat during the sun, trade-offs with, more shade, but more water use. So there's not a perfect solution, and all the solutions are going to be very case-specific and very context-dependent. And then lastly, we're really happy to be in this living laboratory here. These experiments are really important because oftentimes it's just so tough to replicate in the lab what's going on in the real world, because the real world is just so much more complex. And yeah, so we're doing our best to answering all these questions using the tools that we have. And with that, I'm happy to take questions. And then I'll also invite Ankit, Dr. Ankit Joshi up here if you have any questions about ANDI, and then he will guide you on the tour after the Q&A. Thank you.